All right, number 87. Let's see here. All right, on 87, the directions tell us to find capital F prime of x. So what we have is we have the integral from x to x plus 2 of 4t plus 1 dt. Like I told you yesterday, just because we now know the second fundamental theorem of calculus doesn't mean that's always the best way to do it, because that needs to be a constant to use the second fundamental theorem of calculus, doesn't it? Okay? But it's not. So instead, we have a function defined as a definite integral. Let's figure out what that function is. Okay? So we take the antiderivative of 4t plus 1 to get 2t squared plus t, and then we evaluate that from x to x plus 2. So you always substitute in the upper limit of integration first. So I substitute in x plus 2. So I replace t with x plus 2. Then I put a minus sign. And then I substitute in x for t. Then I do some simplifying. Then I do some more simplifying, and some more, and some more, and some more, and some more, and some more. I finally get to here. Well, that's easy to take the derivative of that. So now, could I use the second fundamental theorem of calculus? I could, but I've got to rewrite the whole thing, don't I? Okay? Is 86 the one? Yeah, so look over here at 86. Here's what you'd had to have done. Well, no, I guess I did work it out. Is that, wait, yeah, this one really is 87, isn't it? So here's the way you do it if you do the second fundamental theorem of calculus. I've got to make it so that the lower limit of integration is a constant. So first, I rewrite my integral, make it from x to 0 and from 0 to x plus 2. Now, I don't know that 0 is between x and x plus 2. It doesn't matter. We've always broken the integrals up so that it would work that way. Like if we had an integral from 2 to 7, we'd make it, 2 to 4. Then we could go even 4 to 5, then 5 to 7, then we'd add those up. We'd always do it that way. There's no rule that says you have to. Okay? It just means that, if your lower limit's larger than your upper limit, if you would have gotten a positive area, you'd get a negative signed area. But it's okay. So I can break it up any way I want to. So I chose 0 just because I had to choose something, right? And then that first integral, though, the constant's in the wrong place. It's the upper limit instead of the lower limit. So I have to flip that one over, and remember your integral properties. When you do, you got to change the sign in front of the integral. So finally then, I get here. And now I can apply the second fundamental theorem of calculus. Okay? So the derivative of negative the integral from 0 to x of 4t plus 1 dt, the derivative with respect to x, that is, will be negative and 4x plus 1. So that's a straight application of the second fundamental theorem of calculus. To do the other one, I got to use the chain rule, which we've done, right? So I will end up, what I'm going to end up doing is replacing the t with x plus 2, and then times the derivative of u, which fortunately for us is a 1. Now, I wrote out all the same work we did yesterday, but then we shortened that down, didn't we? We said, hey, it always works this way. Let's jump to the end. So I can do that. That gives me that, gives me that, gives me that. Yeah.
Is it a coincidence that if from the very beginning, you just plugging in like x was a constant?
Yeah, that's a coincidence. Yeah. Lucky's good. Lucky's better than unlucky. All right. Does that take care of 87? What else from yesterday's work?
89.
All right, let's see. On number 89. What are we doing here? We're finding capital F prime of x again. So now this one, I think I do want to use the second fundamental theorem of calculus because the lower limit of integration is a constant, so it's tailor-made for it. I'm going to have to chain rule it though, okay? So I can think of that as the integral from 0 to u of the square root of t dt. So when I take the derivative of that, and again, I wrote all this out, but I can really just cut to the chase, right? That's f of t. So according to the second fundamental theorem of calculus and the chain rule, I'll get f of u times the derivative of u. So that would be f of u, and then that's the derivative of u. Are you okay with that, or do I need to walk you through the steps? Now, and here's the thing. Be able to do this in 2 or 3 steps. Don't forget why it works. Because the AP people will ask you, that you will be asked several questions about the second fundamental theorem of calculus. There's no doubt about it. And they will screw up the notation to the point, they'll put H's and R's and just different letters seems to all of a sudden make it seem harder. Okay? So you got to be able to understand all that so that if the notation messes with you and you're not sure what's what anymore, you can still figure it out. Okay? All right, but does that take care of 89? All right, what else? Anything else from yesterday? All right, back up to the day before when we did 1 through 25. Questions from 1 through 25. 15. All right, 15 and then 23. On 15, the directions tell us to evaluate the definite integral of the algebraic function, and then we can use a calculator to verify. So we've got the integral from 1 to 4 of u minus 2 divided by the square root of u du. Now, there is no quotient rule for antiderivatives. There's no quotient rule for integration. So we need to rewrite this. And what I did was I just divided. Think of that square root of u as a u to the 1/2. So if I've got u to the 1 divided by u to the 1/2, I subtract the exponents. I get a new exponent of 1/2. That's what I get there. Then I've got negative 2 divided by u to the 1/2. Well, there's really no division to do. Just rewrite that as negative 2u to the negative 1/2. That gets me there. I can take the antiderivative of each of those terms. So using the power rule, add 1 to the exponent, make it a 3/2, divide by the new exponent, dividing by 3/2 is multiplying by 2/3. And then for the next term, add 1 to the exponent, now it's a 1/2, divide by 1/2, which is the same thing as multiplying by 2, so I get a negative 4 for that coefficient, evaluated from 1 to 4. So that's the capital F of x evaluated from A to B stage. That's what that is. And that becomes, according to the fundamental theorem of calculus, capital F of B minus capital F of A. And look, I know I wrote x here and it's really u. We got to deal with the notation issues, don't we? We've got to recognize they're going to change the letters. All right? So evaluate first for 4, put a minus sign, evaluate for 1, and then after that, it's arithmetic. Does that help for 15? All right, 23, was that the other one? All right, on 23, the good old absolute value problem here. All right, so we don't have a rule for absolute values, so we got to do something to get rid of them. And remember, if the expression's positive, the absolute value signs don't do anything. You can leave them off. And if the expression's negative, the absolute value signs change the sign. Okay? We always think of it as making it positive. But really, it changes the sign if the expression's negative. So if I set 2x minus 3 equal to 0, when I solve that, I get x equals 3 halves. So 3 halves is where the expression can change from positive to negative or negative to positive. So if x is less than 3 halves, and I really should have said if 0 is less than x and x is less than 3 halves, okay, then what is 2x minus 3? What sign is it? Well, it's negative. How do I know? Well, just pick a number that's less than 3 halves, like 1. If x is 1, 2 times 1 is 2, minus 3 is negative, so it's negative. So the absolute value of 2x minus 3, the absolute value signs change the sign of the expression because the expression is negative. So change the sign in front of it. Put a negative in front of it. Then distribute it. Okay? If x is greater than 3 halves, well, then the expression is positive, so the absolute value signs don't do anything. Everybody with me? All right, so I'm going to break this up. 3 halves is my breaking point because from 0 to 3 halves, I use that as my function. And then from 3 halves to 3, I use that as my function. So now I've got 2 different definite integrals to work in the same problem. It's a little tedious, but that's a fairly easy algebraic function to deal with, so we deal with it. So everybody can get here with me, and then just see if you can follow the rest of it and do the arithmetic. All right. Others from 1 through 25? All right, 24. All right, 24 is the same idea. All right, it's a little harder to figure out what the signs are. So let's see here. If x is less than 3, and how did I get 3? Because if I do that, equals 0, then 3 will be the absolute value of x minus 3. No. How did I get that? How did I decide it was 3? Oh, because it's the absolute value I got to worry about. So, yeah, I just did the absolute value. So, I get 3. All right, so if x is less than 3, then the expression inside the absolute value, the x minus 3, is negative. So the absolute value of x minus 3 is the absolute value changes the sign. So put a negative in front of the x minus 3. So that means that 3 minus the absolute value of x minus 3 changes to 3 minus negative x minus 3. So minus a negative means plus. Well, turns out to be x. So from 1 to 3, I just get that. The integral from 1 to 3 would just be of x dx. All right, if I've got this, I can distribute that negative and make that negative x plus 3, but then I distribute that negative, make that a positive x and a negative 3. All right? Okay. Then, if x is greater than 3, then the expression x minus 3 is positive, so the absolute value sign is not doing anything. So I'll leave it off and simplify. So my next integral goes from 3 to 4, and it's of negative x plus 6 dx. So, you able to follow me to there? Everybody? All right. After we get there, we should be in pretty good shape. So, take the antiderivative, substitute, bunch of arithmetic to do. All right. Any other questions?
Now, if you're doing an absolute value, and when you set it equal to 0, the number that you get not the same.
It will be. Yep.
It's not.
Let's say that 7 was the well, it will be. We could work around it, but I'm not sure I can make one up off the top of my head that will work. I'll probably make one up that won't work. So they'll give you a number that works out okay. All righty. So we okay with the last 2 days worth of homework? All right, that's good. That's really good because these were 2 big days. All right, because we're going to be using these techniques the rest of the year. Now, the second fundamental theorem of calculus, our book kind of drops the ball a little bit on that. And so you will just have to remember how big a deal I'm telling you it is, and I guarantee you it's on the AP test more than once. Guarantee. Okay? So, if you're sitting around with your friends on a Saturday night, you think, oh, what should we do tonight? Hey, we go to the movies. No, I know. Let's review the second fundamental theorem of calculus. That's what you need to do. You'll, all right? Okay. Let's do a few more examples. So back to page 291. Let's take a look at number 34. Page 291, number 34. Our directions tell us to determine the area of the given region. By definition, that's a definite integral. So our equation, our function, our f of x, is y equals 1 minus x to the 4th. So let's write the definite integral that will give us the area of this region. Area equals, then it's the integral from a to b, so in this case, from -1 to 1, of f of x, 1 minus x to the 4th, dx. And we can work this integral and we'll get the right answer. We can take the antiderivative, evaluate it for 1, put a minus sign, evaluate it for -1. It'll work. But you know what is almost always, and I say almost, always the easiest number to work with? 0. Is there any way I can get a 0 as one of my limits of integration? Yeah, this is an even function. Okay, it's symmetric with respect to the y-axis. I can do from 0 to 1 and multiply it by 2. Am I required to do it this way? Nope. But it will make the evaluation a little bit easier. Okay, because I get to substitute in a 0, and at least in an algebraic function, that's almost always easy. Okay, so I'm going to do it this way. I'm going to make it 2 times the integral from 0 to 1 of 1 minus x to the 4th dx. Well, I'm in good shape now. I need to find the antiderivative, so I keep the 2 out in front. So I can use a bracket here since it's capital F of x with a bracket from a to b, so I just put another bracket in the front to keep it looking normal. Okay, so 2 times, now evaluate that integral. So I'll find the antiderivative. Well, the antiderivative of 1 is x. The antiderivative of negative x to the fourth will be negative 1/5 x to the fifth, evaluated from a to b, from 0 to 1. Keep that 2 out in front. Evaluate for 1. Put a minus sign. Evaluate for 0. So you still have the 2 in front. In the first parentheses, 1 to the fifth is 1, times a negative 1/5 is negative 1/5. So I get a 1, I get a negative 1/5. In my second parentheses, 0 to the fifth is 0, 1/5 times 0 is 0, 0 minus 0 is 0. That worked out just like I'd hoped when I rewrote my integral. So 1 minus 1/5 is 4/5. 2 times 4/5 is 8/5. Any trouble with 34? Okay. Let's take a look at number 52. On 52, the problem tells us that the graph shows the velocity of a car as soon as the driver applies the brakes. Use the graph to estimate how far the car travels before it comes to a stop. All right, now, I probably should have got my thoughts straight on this one before I got to it. We know that if we have a function and we take its derivative, if we have a position function and we take its derivative, we get the velocity. And we even know that if we take the derivative of the velocity, we get the acceleration. Okay? Now, we can flip that all around, right? If you have the acceleration, take its integral to get the velocity. If you have the velocity, take its integral to get the position. What's the position function measuring? Distance. Okay? So, distance, so if the position function is, S for position function, is the indefinite integral of velocity, and position functions are measuring distance, then if I put endpoints on there and make it a definite integral, I'll get a number. And what will that number be? It'll be the distance, because that's what the position function measures. Does that make sense? Okay. So the distance then is going to be the integral from when you start applying the brakes to when you stop. So from 0 to 5 of, and then I want it to be of the absolute value of the velocity, because velocity has direction. Okay, now we should be, if we're driving a car, we should be going forward and then slowing down and stopping, and we never went backwards in any of that, right? But it's technically, it's the absolute value of velocity to get the distance. Okay? Now, so that's how I figured out that is the way to approach this problem. Does that make sense to you? Okay. Now, since, and this is the graph, let's see, the graph shows the velocity. So the velocity is always above the x-axis because the car's always going forward, so the velocity is positive. Are the absolute value signs doing anything? That gets me there. That was a nice way to get rid of the absolute value signs, wasn't it? All right. Now, we don't know the function, so we can't evaluate this definite integral by the way that we did the last problem. We can't do the antiderivative, evaluate for the upper limit, evaluate for the, we can't do it that way. Well, remember what we did before we knew how to evaluate a definite integral? We found areas. Definite integrals are areas. Okay? Now, be careful here and look at what these little blocks are. That block has a width of 1/2 and a height of 10. Okay, so you got to be careful for that. So I counted up the squares, and there's about 29 of them. I estimated because some hung over and some were loose, but there's about 29 of them. And each square is 1/2 wide by 10 up. So the area of each square is 1/2 times 10. So if I multiply 29 times 1/2 times 10, I get about 145 feet.
So it doesn't matter if some parts of the area go over the line or under the line?
As far as an estimation, no. I mean, I didn't worry about trying to make this a lower sum or an upper sum. I just counted squares. I mean, look, here's what I did. I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 whole ones. Then, let's see. 23, 24, those two together, 25, those two together, 26, most of a 27. That definitely puts me over 28. That one and that one, 29. Okay? All right. Now, this leads us to a fairly cool idea here. Because look how we found distance. We found it by adding up areas. Okay? Forget about the actual motion of a car for a moment and just look at the graph. Okay? This is the graph of velocity, and we decided that the definite integral from 0 to 5 would give us the distance. So think of integrals as accumulators. They accumulate things. They accumulate areas. In our case, we added up little blocks, okay? They're squares on the graph. They're not actually square, are they, if they're 1/2 by 10? But anyhow, we accumulated little chunks of area, and we added them all up. Integrals, definite integrals, are accumulation functions. They add things up. So, I don't know, sometimes you have a hard time, at least I do, of getting my head around this. I visualize the car applying the brakes, you go a certain distance, and sometimes that gets in the way. Actually knowing what it looks like in reality can get in the way, because once I've got it on a graph, and I've decided that that's the way to figure it out, what does an integral do? It finds area. It adds things up, okay? So even without the function, I can get a pretty decent approximation of that definite integral. Does that make sense? Okay. One more example. Number 57. It says, in exercises 55 through 60, use the graph of f shown in the figure. The shaded region A has an area of 1.5. And the integral from 0 to 6 of f of x dx equals 3.5. Now, before we do number 7, or 57 specifically, let's do a little thinking here. The area of region A, here's region A. And I may do more thinking than is required for this problem, but you've got a few other problems for this graph to work, so bear with me. If that area is 1.5, area integral, so the definite integral from 0 to 2 of f of x, they do call it f, dx, that gives us the signed area, doesn't it? And since that entire region is under the x-axis, if the area of that region is 1.5, would the definite integral equal 1.5? Or would it equal negative 1.5? So the area is 1.5. The signed area, which is what the definite integral really is, has to be negative 1.5, since we can see graphically that the entire region is below the x-axis. Does that make sense? Okay. So if that little signed area there is negative 1.5, and we know that the integral from 0 to 6 of f of x dx is 3.5, what would the area of region B have to be? It's got to be 5, doesn't it? Because if this blue area, if that blue region has an area of 5, when you add the signed areas together, 5 plus negative 1.5, doesn't that give us 3.5? You following me? So that means that the integral from 2 to 6 of f of x dx has to equal 5. Okay? Can we probably answer a bunch of questions about that figure now? Probably. So let's take a look at 57. They want the integral from 0 to 6 of the absolute value of f of x dx. Well, have we worked out absolute value integrals in the past? We'd try to find where it equaled 0, where the expression inside would equal 0, and then we'd break it up. We'd change the sign in front of the negative part, and we would just ignore the absolute value sign on the positive part. So where's that graph equal 0? 2. So let's rewrite this as the integral from 0 to 2 of the absolute value of f of x dx plus the integral from 2 to 6 of the absolute value of f of x dx. I can break I can make it into as many different definite integrals as I want, using as many different limits of integration as I want, as long as when you put them all together, it gives you from 0 to 6, right? Now, since we know that the integral from 0 to 2 of f of x dx is negative 1.5, okay? You can, how do I want to explain this? Now, I'm about to say something. I'm not sure I'm always right. But I'm going to go ahead and say it anyway. I think I'm right. Okay? The absolute value of f of x, taking the absolute value first and then the integral, or taking the integral and then the absolute value, as long as we've got the interval set up right, as long as I know that f of x is either always positive or always negative on that interval. Okay? It can't switch signs anywhere in there. Since I know that f of x in this case is always negative in that interval, does it really matter if I do the absolute value first, then integrate it, or integrate it first, then absolute value it? I got to change the sign one way or the other, right? Since I know it's negative. So we've already figured out that that integral is a negative 1.5. So when you take the absolute value of it, it'll be a positive 1.5. And then from 2 to 6, we'd already figured out that that integral is 5. The absolute value of 5 is 5. So in other words, when they tell us this, when they tell us the absolute value of f of x is what we're finding the integral of, the part of the graph where f of x is positive, leave it alone. But the part of the graph, and I'll try to put it in a color we can see it here, but the part of the graph where f of x is negative, when you put absolute value signs around an expression that's negative, what's it do? Changes the sign. So wouldn't this little green region be the reflection of the red region? The positive reflection of the negative red region? So it's going to end up, I guess what I'm trying to get down to is that has got to end up being a positive 1.5, doesn't it?
What tells us that we are not?
The absolute value sign.
But why would we not?
So see, the signed area is negative 1.5, but they want the absolute value of that, so it's got to be a positive 1.5.
The previous, when we're dealing with that, we got to get absolute value, separate it.
Well, that's what we did here. We did the same thing. We found where the function changes from positive to negative or negative to positive. So that's how I got the 2 for there and there. So this one, so think of, that's why I tried to explain it 2 different ways, and I guess I didn't explain that I was trying to explain it 2 different ways. We're all cool with that one, right? From 2 to 6, we can ignore the absolute value signs completely because f of x is always positive. Okay? So let's forget about that and let's concentrate on this other one. When I take the absolute value of an expression that I know is negative, turns it positive, which is what you always want to say. I always say, it changes the sign. You always want to say, turns it positive. So let's think of it that way. Turns it positive. So that's how I go from having this as my graph of f of x. I go from having that as my graph of f of x to having the reflection of it as my graph of f of x. So if the area of that region, they told us it's 1.5, so forget signed areas for a moment. If the area of that region is 1.5, doesn't the area of the green region have to be 1.5?
I'm just applying it. Okay.
Because they gave me the absolute value sign. If they hadn't have put absolute value signs on there, I would still set it up the same way. I'd still say the integral from 0 to 2 of f of x dx plus the integral from 2 to 6 of f of x dx. But I would get negative 1.5 here and positive 5 here. Absolute value signs there, absolute value signs there. Absolute value signs there, absolute value signs there. Yeah. Correct. Yep. Yep. You always want to deal. Well, kind of like before when we had the triangles and rectangles and things for the weird looking graphs. We'd break it into chunks we could deal with. Same idea. Break it into chunks you can deal with. Okay. Maybe I should have started the whole thing this way. That's probably going to make things worse, right? But maybe I should have started this way. If that's our graph of f of x, and we take the absolute value of it, it turns positive positive, or turns negative positive, and leaves positive alone. So if I can, let's see, watch this. This would be cool if it works. And can't get that to pop up, so it won't be cool because it won't work. I'll just do it that way. If I turn my graph of x into that, okay, so that's what it looks like when it's just f of x. But that's what it looks like when it's the absolute value of f of x. I should have started that way, shouldn't I? Does that make more sense? It does to me.
Makes sense. I don't see the difference between this one.
There's really not a difference. The only difference is on 23 we had a function, so we found the different parts by doing the antiderivative using the fundamental theorem of calculus. This problem we could have worked before Christmas. That didn't help, did it? We'll think about it. Maybe I can explain it better next time. There's what you need to be working on. Page 291, 27 through 42, and 51 through 59. Ask.
How, or when should we, or how do we know when to consider this as opposed to just plugging in the first?
The only time the second fundamental theorem of calculus comes along is applicable is if you have a function that's defined as a definite integral and you have to find the derivative of that. That's when you do the second fundamental theorem of calculus.
What's the example of one?
All the others. When both of your limits of integration are constants.